Good afternoon, all the students. We'll proceed with our fourth lecture. Okay, in the previous session, we have seen how perceptron training rule can be learned. Will guide the neural network in order to learn how to adjust the weights. Okay, so this perceptron training rule, we understood it as W is equal to Wi plus delta Wi. Okay, this is the training rule which guides any artificial neural network perceptron in order to adjust the weights to reach the ideal target function. Okay, so this is the old weight. This is the change that has to be done to the weight in order to give a new weight. This weight should be able to reduce the prediction error. This new weight which is adjusted should be able to reduce the prediction error, right? And for linearly separable classes, perceptrons use perceptron training rule, and for non-linearly separable classes, they use gradient descent and the delta rule. For that, we have seen that as a sum squared error of all the predictions, TD minus OD whole square, where D is every training example, and add up all of them and make it as half. That is the error measure on the vector W, right? This is the gradient descent and the delta rule. This is used to measure the error in non-linearly separable problems. Perceptron training rule is the algorithm used for linearly separable problems in order to adjust the weights to reduce the prediction error, and gradient descent and the delta rule is the error measure which is used to reduce the error in predictions with respect to non-linearly separable problems. Okay, this is what we understood in the previous class. Now let us see, though I have given an introduction to this visualizing the hypothesis space, I'll repeat that once again for you so that it will be very clear. You should be very clear about the terminology I use there. Okay, so if you have any doubt or you didn't understand a particular term, ask me. I'll go very slowly. Okay, and then we'll see the derivation of the gradient descent rule. Now, how a hypothesis is visualized when we come to gradient descent algorithm. As I told you, gradient descent is compared to or is analogous to mountain descending problem of a person without a compass and almost blindfolded, right? So in that case, when he starts here, he has to go forward towards the mountain. He has to go downhill, right, towards his destination. Say this is his destination. Now he starts from here. How to start again? He doesn't have any compass, so he searches around him. Which area is having the maximum steepness, inclination? Means say this is the mountain. If I put like this, inclination is very low. If I put like this, inclination is very high. Inclination is nothing but the slope. Okay, so this person will check for the maximum slope around him. That is called as the local minimum. In the same way, let me compare that to you. Let me compare that with this problem. We are starting with random weights initially. Okay, we doesn't know what are the optimal weights. We are starting with some random weights. Here he is starting with some random direction. Here we are starting with some random weights. Okay, now we are trying to reduce the prediction error. So at each step, okay, so this somewhere some prediction is made. Now weights are adjusted in a way to reduce the prediction error. Okay, so if you want to fire a positive output, you may have to increase the weight. If you want to fire the negative output, then you have to reduce the weight in such way, based on the context. Okay, it is not always like that, but based on the context, this algorithm will make the weight adjustments. But initially, it doesn't know what is the optimal weight. Okay, it goes randomly, starting with some random weight, right? So it goes forward. Now it checks the prediction error again here. Now, if the prediction error is high, then it may just change its direction because it may be away from the global minimum. Okay, if the prediction error is low, yes, it may be going in the right direction, so it proceeds further. That is what this person is doing on the mountain, right? He goes further, again checks his local minimum, again checks his local best move. Where the steepness is high, in that direction, where the inclination is high, in that direction he moves forward. Okay, he is descending with some gradient, with some measure, right? In the same way, here also the weights are adjusted. Okay, by adjusting these weights, yes, there is reduction in the prediction error. Then go forward, check the weights, check the prediction accuracy again. Yes, there is lesser prediction error compared to the previous step, means it is going in the right direction. Model is being trained in the right direction. Yes. Now, as it comes to the global minimum, this is the global minimum, right? See this, compare this graph, compared to this side, this side, this side, wherever you see, what is the bottommost point? This one, right? This is called as the global minimum. At each step, it takes some decision, right? In order to proceed further, the model to proceed further, it takes some decision at each step. That is called as local minimum, means local optimal solution. Locally optimal solution it is taking and proceeding further to reach this global minimum. Okay, now you are comfortable with local minimum term and the global minimum term, students? Local minimum helps a person descending a mountain to take his next step, but global minimum is his final destination, right? In the same way, here the prediction accuracies at these points are little higher, but when finally it reaches its destination, there the prediction accuracy must be prediction error. Just replace my term with prediction error. It will try to minimize the prediction error as much as possible. So this is the place where the prediction error will be minimum. Okay, so this model is being trained to reach this minimum, global minimum, where the prediction error is very low, where the prediction accuracy is very high. Okay, so this whenever we visualize a hypothesis space in this gradient descent algorithm, it looks like a parabola like this, where it is touching the surface, the minimum point, that is called as the global minimum. Got it? To understand the gradient descent algorithm, it is helpful to visualize the entire hypothesis space of possible weight vectors and their associated e-values. E-values means error values. Okay, so the weight vectors are plotted on x and y axis, and the error is plotted on z axis. It is a three-dimensional space. Okay, we are having three dimensions. On two dimensions we have the error, the weights, and on the third dimension we have error associated with those weights, right? Now this can be treated as a gradient descent problem. Now I'll make it more clear for you. Here the axis W0, this axis, and W1, this axis, represent possible values for the two weights of a simple linear unit. Let us take the linear unit as W1x1 plus W2x2. We have, W0 x0 and W1 x1. Only two weights and two input units you have. Okay, now in that case, if we can plot this W0 on x-axis and W1 on y-axis and error on the z-axis, this one. Okay, the W0, W1 plane therefore represents the entire hypothesis, correct? Our hypothesis is what? Optimal weights, optimal combination of weights. So the hypothesis will contain how many weights here? There are only two input units. So two weights will be associated with them. That is W0 and W1. Now the vertical axis indicates the error E relative to some fixed set of training examples. For every training example, the prediction error is calculated. For every training example, the prediction error is calculated. Sum square all of them and divide by 2, you will get this error measure, right? Now the error surface shown in the figure thus summarizes the desirability of every weight vector in the hypothesis space. We desire a hypothesis with minimum error, right? How should be our hypothesis? Our hypothesis should be ideal target function. It should minimize the error that is encountered by the model. That is why we have taken this as a layer. Did you observe this entire one? We have taken this as a layer just to show you how we start with random weights, how you try to reduce the error by altering the random weights, and finally arrive at a minimum prediction error, that is the global minimum, this point, right? Given the way in which we chose to define E, for linear units, this error surface must always be parabolic, as we said, with a single global minimum. You can't have something like this because this entire thing will give you local global minimum, and it has many values, means many hypotheses. It should not be like that, okay? It should have one single point. If you take a curve like this is one single minimum, right? That is why we are indicating the ideal hypothesis space in this gradient descent algorithm as a parabola, which will have only one single global minimum value, right? So the specific parabola will depend, of course, on the particular set of training examples. How does this parabola depend? How does the shape of this parabola depend? On the particular set of training examples, how the training examples are provided to the model to be trained on those training examples, learn something in order to reduce the prediction error. This parabola will depend on those training examples. Now, gradient descent search determines a weight vector that minimizes the error measure. Okay, E is the error measure by starting with an arbitrary initial weights, right? Initially, we don't know what are the weights. The model doesn't know what are the weights. So it will start with some random weights, say 2, 3, 4 or 5, 6, 7 like that. Then repeatedly modifying it in small steps. That step is called as the learning rate. Okay, I gave you very clear example of learning rate in the morning class. Repeatedly modifying it in small steps. It has to take small steps, modify it and again check, modify it, again check, modify the weights. If it makes larger modifications, it may miss the ideal target function to the other side, which will make it miss the ideal target function. So just check. Say you want to reach 0.5. You can start with 0, I said. Now, you will make incremental steps as 0.5, 0.1, 0.5, 1, 1.5, like that. Okay, but initially, if you make steps like this, 0.8, suppose, then add 1.6, then add 2.4, add 0.8 each time, then add 3.2. Now you are reaching your solution or the goal, that is 5. Now after 8 4 32, 8 5 is 40. Now you make add another 0.8, it becomes 4.8. Now add another 4.8, it becomes 4.8. Now if you take the same big step and add another 0.8, what will happen? It will become 5.6. Did it miss the target 5? It crossed the target, right? That is why when it comes approximately to some distance closer to the target, after 3.2, let it add 3 points at a time instead of 8 points. Okay, so instead of adding 0.8, if it adds 0.3, then it can be 3.5. Then add another 0.3, it can be 3.8. Like that, slowly it is approaching the target 5. Right? Did you understand now? Learning rate, this 0.8 and 0.5, I call it as learning rate here, because 0.8, it is taking further step. Again, 0.8, it is taking further step. But after that, when it is reaching the destination, it should not use larger steps. That is why it is reducing its steps to reach the destination appropriately without crossing it. That is why this points what we add, we call it as learning rate. That learning rate should be reduced and reduced to minimum as it reaches its destination, in order to not miss the destination, in order to not miss the optimal target function in our case. Okay, so at each step the weight vector is altered in the direction that produces the steepest descent along the error surface depicted in the figure. We have seen this, right? This is called as the error surface. Now this error surface have to be reduced, and it should reach the minimum error, which is called as a global minimum. Got it? Initially our error is very high. Then we try to reduce the error by adjusting the weights. Then we try to reduce the error by adjusting the weights. And finally we reach the global minimum. That is the ideal target function that has to be reached by the model in order to work efficiently with unseen data, in order to make predictions which are highly accurate on unseen data. Okay, that is why we are calling that parabolic mesh as error surface. Okay, at each step the weight vector is altered in the direction that produces the steepest descent. Steepest descent means reducing the error, steepest reduction in the error, that is called as steepest descent. Okay, steepest descent along the error surface depicted in the figure. This process continues till the global minimum error is reached. Okay, in this case, what is the global minimum error? This one. Until this point is reached, it keeps on adjusting the weights. Once this global minimum is reached, there is no prediction error. Prediction accuracy is very high. At that point, the model will stop adjusting the weights, and that linear equation is the ideal solution for the model in order to generalize on new data or unseen data. Okay. Now let us go to next topic, derivation of the gradient descent rule. It is very easy. Actually, I saw this derivations and I thought how to convince the students. But when I actually studied it in depth, it is very easy to understand. Okay, listen carefully. Don't sleep, students. You are awake, right? How can we calculate the direction of steepest descent along the error surface? Okay, our error surface is like this. Our the model error surface is like this. So this is the global minimum, and the model starts somewhere from here, and it has to reach by checking its local minimum forward to reach this global minimum. Okay, now how can we calculate the direction of steepest descent, whether in this direction or in this direction or in this direction? Means actually what? The direction of steepest descent is nothing but the direction the direction in which the model can reduce the error, prediction error. That is the direction of steepest descent. Because we are understanding it with respect to mountain descending example, we are calling it as steepest descent. Steepest descent is to reduce, steepest reduction in the error. How do you calculate in which direction should the algorithm proceed to reduce the error to the maximum? Okay, that is called as steepest descent. Now the algorithm started here in this way. Now it will check in which direction, if it goes, it will get the smallest prediction error. Okay, So how that is calculated? This direction, this steepest descent direction, can be found by computing the derivative of error measure E with respect to each component of the vector W bar. What are the components of W bar? W0, W1, W2, and so on up to Wn, right? You know that vector is combination of various elements. Now this weight vector is combination of W1, W2, W3, and so on. Now this direction of steepest descent can be found by computing the derivative of E with respect to each component of the vector W bar. What is derivative? Derivative is studying the impact of one variable with respect to other variable, right? Studying the impact of independent variables on dependent variables. Say x1, x2, x3, these are independent variables, and these will help us determine the dependent variable, that is the prediction. Okay, if it is classification, yes or no. If it is continuous variable, something like a number, sale price of a house, or weather forecast in the next 2 days, that is y. That is called as dependent variable. This dependent variable is being estimated by the independent variables, combination of that independent variables. Now you are trying to measure what is the impact of each of them on y, or if you have weights, what is the impact of each weight on y. For that, in order to study that impact, you are using mathematical derivative. Okay, again partial derivative and full derivative. What is partial derivative? If you have many vectors to be studied, in that case you use partial derivative. If you want to study the effect of only one vector or one variable, then you can go for full derivative. Okay, now partial derivative is used is denoted by dou. You know what is dou, right? Partial derivation, dou. Okay, so this vector derivative is called the gradient of E. You are trying to reduce this gradient. You are trying to descend. Gradient descent means what? You are trying to reduce the gradient. You are trying to reduce the error measure as you reach the global minimum, where the error is very, very less, which denotes the global minimum, or ideal target function, where the prediction error is almost nil. Okay, now this vector derivative is called the gradient of E. You are comfortable with this term, students? Gradient of E means gradient is some change that has to take place in E in order to reduce that error. Okay, you're trying to descend the gradient, you're trying to reduce the gradient of the error. That is why it is called as gradient of E. Measure, it is simple measure. Okay, you're trying to reduce the error in this measure of E with respect to what? With respect to all the weights. Now how do you represent that? See this, this is important. You represent this gradient of E as inverted delta symbol. Did you notice this symbol? Inverted delta symbol. Delta represents change. Inverted delta represents gradient. Okay, that is also change, but we are trying to reduce the error. Okay, delta, this represents either increase or reduction in the value, but here we are trying to denote gradient descent. That is why we are using inverted delta, means the gradient of E with respect to the weight vector W bar. Now how do you denote that? How do you denote that vector derivative? The vector derivative or the gradient of E, listen to my usage of terms when I am trying to denote something mathematically. That is very important, right? You can't simply say inverted delta E in the brackets W bar. No, read it in a formal way, because if you read it in that way, in exams you will be able to represent it better. Okay, so this vector derivative of E, or the gradient of E with respect to the weight vector W. Don't call it as W bar, call it as with respect to weight vector W. That is nothing but it is equivalent to, how can we represent that? Partial derivative of E with respect to W naught, partial derivative of E with respect to W1, and so on up to Wn. This you understood clearly? We are finding out the derivative. We are finding out effect of W naught, W1, W2, the weights, effect of the weights on the error. This weight adjustment is giving this error. After adjusting the weights, it reduces the error. Means you're trying to study the effect of these weights on the error, whether it is increasing or reducing. When this error measure reduces to the minimum, that is the optimal set of weights you need to consider, or the model need to consider, in order to make good predictions with good accuracy. Okay, so that is why we are representing like this: gradient of E, or vector derivative of E with respect to with respect to weight vector W, as partial derivative of E with respect to W naught, partial derivative of E with respect to W1, and so on up to Wn. Each weight vector's influence on the error measure is being calculated. That's all. That is what we mean by this partial derivative. Okay, now we'll go forward. Now notice this gradient descent of E with respect to the weight vector is itself a vector whose components are the partial derivatives of E with respect to each of Wi. That is what we have seen, right? This is the partial derivative vector with respect to each of the weights. Now, when interpreted as a vector in the weight space, the gradient specifies the direction that produces the steepest increase in E. Okay, so it will try to the gradient will try to specify the direction that produces the steepest increase in E. In which way it is increasing the error. In that way, it has to avoid. Go in the negative direction. And again, this matters. If you want positive predictions, go in the positive direction. Means steepest decrease. If you want negative values, steepest increase. In that way, you have to proceed further. Now, the negative of this vector, therefore, gives the direction of steepest decrease. This is what I said. If you want steepest increase, means you want the negative side, you have to go in one direction. And if you want steepest decrease, you have to go in other direction. Say mountain climbing, if you see, it is steepest increase you want. But when you're descending a mountain, it is steepest decrease what you want, right? In that way only you can understand the reduction of prediction error also. You have to work in the direction, the model have to work in the direction which will reduce the prediction error. That is its final, ultimate objective. Okay. So for example, the arrow in figure shows the negated gradient delta E W bar for a particular point in the W0 W1 plane. I'll just go back to this hypothesis space. See, in this direction, did you see this arrow? It is trying to reduce the prediction error. Here the prediction error is more. It is trying to come to this place where the prediction error is less. Okay. So it is trying to reduce, come in a negative direction, negated gradient, in order to reduce that particular prediction error. That is represented by this negated gradient, delta, inverted delta, that is the gradient error with respect to weight vector W. Now, since the gradient specifies the direction of steepest increase of E, The training rule for gradient descent is, now if you take the perceptron training rule, you know that rule, right? The weight adjustment to be done by for W is nothing but the old weights plus the new weights, the change in the weights, that will give the new weights, where instead of plus now you are taking negative. Why? Because you are coming downwards, you are trying to reduce the weights in order to reduce the prediction error. That is why you have given minus here. You know this formula, right? Minus learning rate multiplied by this error, gradient error. That will be your change in the weight values. Okay. If you take perceptron training rule, if you want to fire positive output, you increase the weight. If you want to fire negative output, you reduce the weight, right? Same concept is being applied here. If you want to calculate the steepest increase of E, means in a negative direction, then that is given by this minus learning rate instead of plus learning rate. Okay, here nu is a positive constant called the learning rate, which determines the step size in the gradient descent search. Because you're descending, it is coming down, it has taken a negative symbol. But if you're going up, it will take a positive symbol, or adjusting the weights. That is mainly with adjusting the weights. Now the negative sign is present because we want to move the weight vector in the direction that decreases E. Error has to be reduced. When error has to be reduced from weight, something have to be removed, right? That is why it is taking a negative sign in order to adjust the new weight. Got it? So this training rule can also be written in its component form as, it can directly be written like this, right? Initially we have taken in this place gradient error with respect to the weight vector. Okay, now in this place we have used the partial derivative. That's all, no more change. Okay, so the delta Wi, the change that has to be made to the weights is, because it is gradient descending rule, you are negating it. You are giving a negative sign to it. That is why you have used minus learning rate, and this gradient error can be denoted as a partial derivative with respect to the weight vector Wi, right? That is why we have given dou E by dou Wi. Wi can be right from W0, W1 to Wn. Okay, that is why it is given as the partial derivative, which makes it clear that steepest descent is achieved by altering each component Wi of W bar in proportion to dou E by dou Wi. You have to alter the components, weight vectors, by in proportion to dou E by dou Wi. In proportion to means what? If this weight is having highest impact on the error, reduce that. If that weight is having lowest impact on the error, increase that. Like that, weight adjustments have to be done. Now, to construct a practical algorithm for iteratively updating weights according to this equation, delta Wi written as minus learning rate multiplied by the partial derivative of the weight vector, we need an efficient way of calculating the gradient at each step. For that, let us write some algorithm. Okay. Now the weight vector of dou E by dou Wi, the partial derivative with respect to the weight vector, the vector of these derivatives that form the gradient can be obtained by differentiating E from the equation. Let us take this equation and apply the partial derivative. Okay. This equation, you remember, delta rule. For non-linearly separable problems, we use delta rule, and that delta rule is the sum squared errors in the predictions divided by 2. Okay, that will give you the error measure on the weight vectors. Now, let us apply derivative on this particular equation. Okay, so when we apply derivative, just apply dou derivative of E divided by dou of all the weight vectors Wi. I where I is equal to 0, 1 and so on up to n. Okay, so you are applying the partial derivative on this equation. Dou E by dou Wi equal to, apply on this side also. Dou by dou Wi, write this equation as it is. But you know that constants doesn't have any impact on the dependent variables. Constants doesn't influence the equation in any way. That is why remove this constant out. Take out this constant out. And sigma is an operation. Even that you have to bring it out. And apply this dou directly to this part. Okay, dou by dou Wi. Which one you are differentiating? Partial differentiation on TD minus OD, that is the prediction error square. Okay, you're finding that now. And how you do whenever you do a differentiation for a term having square, that 2 will come to the front, right? So that 2 is taken, and one of those terms TD minus OD is also written. TD minus OD is nothing but TD minus OD into TD minus OD, right? So take this term along with this square, 2 into TD minus OD, and apply the derivative, apply the differentiation on the remaining term, that is TD minus OD. TD is the target label of the training example. OD is the prediction of the prediction made by the model for that particular training example. Now, what is the difference between them is that prediction error, right? So you're differentiating that. When you differentiate, before that, this 2 and this 2 gets cancelled. Okay, so remaining TD minus OD term and the partial differentiation of TD minus OD. In that case, you have only with respect to weight vector, right? So with respect to weight vector, if you take OD is represented as a linear combination of weights and their associated inputs. Do you remember this? In the delta rule, we try to represent the output as the combination of the weight vector and the input vector. You remember this? That we have substituted here. For what is prediction? How is the prediction made? Only when you have a linear equation with this, right? W1x1 plus W2x2 will give you the prediction 0. O. That is the output of the linear equation, which is the prediction. Okay, so this prediction error can, this prediction can be substituted with this W1x1, W2x2 written as W bar x bar. Can you substitute? That is substituted here. OD is substituted with weight vector W dot each training example's input. Okay, because you are taking OD. If you take O, it is W bar x bar, W vector x vector. But if you take OD, then you are referring to a specific training example. That is why you are giving W bar dot XD bar, W vector dot XD vector. Okay, now this can be differentiated like this. TD, it doesn't have anything with respect to WI. So this is totally removed. This is not considered at all. Now, WI, when it is differentiated, when W bar is differentiated with WI, that term will become 1. So what is remaining? Minus XD bar. That minus XID bar is given here. Why we have taken I is the differentiation that is left with the weight vector. That is why we have taken XID instead of XD. We are trying to study the effect of WI on XD. But when we are differentiating, it doesn't have any term common with W except this I, which represents that particular ith training example. Okay, that is why it has given minus XID. Now see, dou E by dou Wi, that is the partial derivative with respect to the weight vector, now has turned into sigma D belongs to D, TD minus OD. This is the term which came to the front before differentiation, and after differentiation you get minus XID. W will become 1 when you do the differentiation. Same terms, right? When it is differentiated, when XD is differentiated with WI, it will get the ith term, but W doesn't have any effect on X here. That is in derivation, in the differentiation. Okay, so you get minus XID, right? So this is your final derivation. This is your final derivation, where XID denotes the single input component Xi for training example D. That is why we represent it as XID. It denotes the single input component Xi for the training example D. Among all the training examples, capital D. Okay, now we have an equation that gives dou E by dou Wi in terms of the linear unit inputs XID, outputs OD, and the target values TD. You have all the terms, right, associated with the training examples. This equation has all the terms now derived. Now substituting equation dou E by dou Wi equal to this equation, what we got as a result of the derivation, into the equation, the change, delta change that has to be made to the weights, that is minus nu dou E by dou Wi. Now in this dou E by dou Wi place, let us substitute this equation. This yields the weight update rule for gradient descent. What is the update rule? Final update rule we got, delta Wi can be calculated as nu multiplied by summation of all the prediction errors into the input value for each training example. This is how we need to understand the final derived gradient descent rule. This is almost same as your perceptron training rule. Do you remember the delta Wi is calculated as nu T minus O Xi, right? This is almost the same, but we learnt it, understood how it is actually derived. Now to summarize, the gradient descent algorithm for training linear units is as follows. How actually the steps will move. Let us see. Pick an initial random weight vector. We know that. Let us start with some random weight vector. Apply the linear unit to all training examples. Then compute the change that has to be made to the weight for each weight according to equation 1. What is our equation 1? This one. According to this formula, the model will calculate what change have to be made to the weight delta Wi. That change is calculated by using this equation 1. Okay. Now that is added to the old weight in order to get the new optimal weight. Now update each weight Wi by adding delta Wi, then repeat this process. Because the error surface contains only a single global minimum, right? This is the error surface and this is the single global minimum. This algorithm will converge to a weight vector with minimum error, regardless of whether the training examples are linearly separable, given a sufficiently small learning rate nu. Okay, so irrespective of whether they are linearly separable or not, because it has only one global minimum, it has to reach that destination, though it takes several iterations if the weights are not adjusted properly. Okay, If nu is too large, what will happen? The gradient descent search runs the risk of overstepping. Sometimes it may cross and go off in this direction, overstepping the minimum in the error surface rather than settling on this particular value. That is why learning rate should be smaller, smaller, smaller as it reaches the global minimum. Okay, so that it doesn't overshoot the minimum value and cross the value and go to the other side. Now, for this reason, one common modification to the algorithm is to gradually reduce the value of nu, the learning rate, as the number of gradient descent steps grow. Okay, after certain steps, reduce the learning rate. After certain steps, reduce the learning rate so that it settles at the global minimum without missing its ideal target function. If it misses, then we may not be able to come back. Why? Because it has gone to the other side and it is trying to find out again local minimum. Okay, so it doesn't reach the global minimum at all. That is why the learning rate should be optimized so that it will reach the destination without overshooting it. So this is the last slide. The gradient descent algorithm, what I have explained in the previous slide, same thing is put into steps, algorithm steps. This gradient descent algorithm takes the training examples and the learning rate as input. Now each training example is a pair of the form x vector having lots of attributes and t the target value. That is what given here. X bar is the vector of input values and t is the target output value. Nu is the learning rate. You can fix it somewhere around 0.05. Later you can reduce it to 0.01. Later you can reduce it to 0.001 in order to arrive at the perfect global minimum or approximation of the global minimum. Okay, now initialize each wi to some small random value. We start with some random weights. Okay, now until the termination condition is met, repeat what? Initialize each delta wi to 0. Initially assume that there is no change in the weights, so delta wi will be 0. Now for each training example x bar t, repeat what? Input the instance x bar to the unit and compute the output O. Compute the prediction so that you can see what is the prediction error, right? Input the instance x bar to the unit, that is the perceptron unit, and compute the prediction. Compute that perceptron unit's prediction, what it can make. Now for each linear weight wi, what you have to do? Calculate the change that you have to make to the wi. How is that change calculated? Delta wi plus the learning rate multiplied by the prediction error multiplied by the input value. Now, for each linear unit wi, repeat, what has to be repeated? Adjust the weight. Linear unit means what? W1, x1 is one linear unit. W2, x2 is one linear unit. W3, x3 is one linear unit. Now, for each linear unit, adjust this weight as calculated as W1, delta W1, delta W2, delta W3. Delta W1 is added to W1, delta W2 is added to W2, delta W3 is added to W3 to get the new weights. Now again, prediction is made. That is why see, repetition is done again and again iteratively. These weights are adjusted until the prediction error reaches its minimum point where no longer there is any prediction error. Okay, that is called the global minimum. It has reached there, that is its final destination. That is where the algorithm stops adjusting the weights, and that combination of linear units W1, X1, W2, X2, that is your ideal target function. Got it? This is how we can understand gradient descent algorithm. In the next class, we'll see stochastic approximation to gradient descent. Students, I request you to go through this content in the textbook by listening to the lecture at the same time, so that you will have control on the topic. If you don't understand this, Further 3-4 topics are there, you will not understand any of them. That is why, at least till here, follow my first 4 lectures, understand the concepts and be ready for the next concept. Okay?
Okay, ma'am.
Yes, good. We'll meet in the next class. Bye.